Thank you. Please have a seat. Thank you. So Trevor, thank you for joining us. You flew from Vancouver, Canada.
I did.
To help us, and I'm very pleased to have Trevor because he's certainly one of the most experienced executives in the quantum industry. We just talked about AI and trying to understand how AI could be deployed at scale, and here it is. Quantum is coming. So Trevor, can you say a few words about yourself and your company?
Yeah, great. Happy to be here. Thank you for the time. I am the Chief Development Officer at D-Wave Quantum. I lead the research and product development teams at D-Wave. And our mission at our company is to put quantum computing technology in the hands of our customers to solve their hard problems. We've been working on quantum computing technology for the better part of 2 decades, and we are the first to commercialize quantum computing technology.
I think you're very modest. I would say, your company went public. Your company is a processing workload of real customer every day, if I may say so. We told me that you have almost 100 customers working with you. So what is real in quantum? That's a big question here. Where is the hype? What is real?
Yeah, that's a great question. I think one of the things that everyone should keep in mind when looking at the quantum industry is there's different approaches and different technologies that are developing at different rates. At D-Wave, we chose to focus initially on annealing quantum computing because we saw this as the fastest way to a commercial technology. And that bet has paid off. Like Eric said, we actually have production customers that are running production workflows, optimizing their business with our technology on our cloud platform. Annealing quantum computing technology is proven to be easier to scale up, and there's a natural fit between annealing systems and hard business optimization problems. For example, whether you're an airline, for example, and you're trying to schedule flights, match planes to routes, that's an example of a hard optimization problem that doesn't scale very well as your business complexity grows. So we have multiple customers that are actually finding value and getting ROI on using our technology to optimize their business operations. There's other approaches to building quantum computing. So another approach is what's the so-called gate model approach. That is very much in the R&D phase. That's very promising. We have our own gate model effort. We're actually the only company that has a dual platform approach where we're building annealing and gate technologies. The real killer app and what we're excited about with the gate model direction is in quantum chemistry, materials simulation, the ability to build molecules and to build materials within your quantum computer to model their behavior well ahead of fabricating them. And I think there's a huge upside there, but there's still quite a bit of development that needs to be done.
I think we're living in a world where we are basically stormed by technology, and AI has learned all of us to focus on use cases. Can you give us a couple of customer use cases today with your system?
Yeah, absolutely. Like I said, optimization it crops up across a broad range of enterprise and government businesses. There's a kind of a broad umbrella of use cases that we're calling quantum optimization. So things like supply chain scheduling, logistics, how you use finite resources to basically run your business. A good example of a customer that we have currently running production operations or business operations with our Leap Cloud platform is Ford Otosan. So they're an automotive manufacturer in Turkey, and they're running a production line that's heterogeneous. So their production line can build vehicles of different types, and they need to switch the production line back and forth. And they have a hard business problem that they want to actually run this production line in a way that minimizes the downtime involved with swapping back and forth, but they still want to meet demand. They want to meet the specific demand for vehicle production. They need to schedule this with respect to supply chain constraints. There may be supply chain fluctuations that guide their production, and there's maintenance and just overall operations of the actual factory line. And so they had a classical approach to solving this problem that took over half an hour to do sort of several thousand vehicle production runs, that using our technology got down to under 5 minutes. So now they can actually run and optimize the production line much, much more often. But even more importantly, they had to really remove a lot of the complexity of this business problem with traditional traditional approaches, and they could layer all that complexity and those business constraints back in using our annealing quantum computing technology. So this is an example of us being able to deliver value directly and a customer getting ROI and actually being able to run their business better.
So I'm going to push you a little bit. You know, we talk about outcome. Can you give us all the magnitude of the ROI given by your customer? Are we taking millions, tens of millions?
Yeah.
Millions?
Yeah, that's a great question. I mean, it really depends on the use case and the customer. I mean, the value that the customer often will get is primarily around, can I actually solve my problem faster? Can I represent the full business complexity of my problem? And do I get better quality answers? And so for a lot of the time, our customers aren't directly sharing the ROI that they get with us, but they are definitely getting a return of investment. And again, it varies with the specific use case and the optimization problem.
So you have experience with customer. We understand, for example, in AI, there is an issue where is the enterprise, is the customer ready to absorb AI? Now, with your experience, what does it mean to be ready to absorb this quantum solution? What does it take as a customer?
Yeah, that's a great question. So we've put a lot of investment into the tooling. We have an open source tool set written in Python where any developer that has some basic understanding of Python and actual operations, research and business operations can quickly formulate for our platform. It's been critical that we make the technology accessible not just to people that have backgrounds in physics and computer science, but to broader developers. Broadly, to become quantum ready, you need hard optimization problems that you've identified, that you either are struggling to solve now, solving suboptimally, are really representing a pain point in your business, and then access to data sets. So data sets that are encapsulating sort of the crux of the hard problem that you can actually use to prototype these problems and to prototype solutions for our technology. We also have a professional services team, and this is really the route for success for a lot of our production engagements or production customers, is they work closely with internal experts that have done formulations for similar business problems for other customers.
Thank you very much. So basically, you're creating for the quantum the equivalent of the forward development engineers in AI. That's a new buzzword, to have engineers helping the customer to fix problem. We've seen a lot of momentum recently in AI, especially in the last 12, 18 months. The stock market was a bit hyping on AI. There have been announcements. A couple of companies went public. You can argue whether it was too early, that only the future will tell. What has happened? Why suddenly people are so excited since 12 and 18 months?
Yeah, that's a great question. I think there's two reasons why the quantum industry and quantum computing have sort of caught attention more broadly. The first is that there have been some fundamental advancements and breakthroughs in the technology and the hardware. I mean, we at D-Wave published about a year and a half ago a result that we call quantum supremacy on a real world problem, where we used our annealing system to do a material simulation. And we benchmarked that against a Frontier supercomputer, an exascale system that is installed at Oak Ridge National Lab. And we showed that the calculation and a material simulation sort of a problem could be solved on our system in a matter of minutes, and we would project that we would take over 1 million years on this exascale supercomputer. So there is now a fundamental gap opening between what quantum systems can do and how classical systems are going to be able to catch up, and that gap is only widening. And that really is sort of like a fundamental breakthrough over the last couple of years. And Google as well has made, I don't know if you had followed the announcement about a year and a half ago, but Google published a breakthrough in error correction, which fundamentally advances gate model quantum computing. And so I think both of those two things are kind of catching the attention of the world, just fundamental progress. But the second thing, Eric, is, it comes from the industry and the AI boom. I think a lot of people are realizing the computational bottlenecks that are arising as we try to train larger and larger models, these frontier models. There's a huge build out of data centers and a huge demand for compute. And this is really where I think the quantum industry can potentially benefit the AI industry. I see these as complementary technologies. We're offering an energy efficient way to solve hard problems with quantum computing. And I really think that will enhance AI applications and hopefully bend that cost curve in terms of that computational bottleneck.
So I hear about energy efficiency, I hear about computing efficiency, I hear about more tools to help the developer to use it. So obviously on the other side, you have NVIDIA and the servers and the data centers and CUDA. Where will it be the integration point in your mind? You know?
Yeah, I mean, I really see our quantum computing systems as similar to the GPUs in terms of the trajectory. They're able to accelerate really important workflows that other approaches are really struggling. I mean, you're not running, say, Windows on a GPU, for example, but you are pairing CPUs and GPUs together and using them each in their sweet spots to solve a harder problem. The same thing will happen and is happening as quantum computing, as QPUs actually mature. You'll see QPUs, CPUs, and GPUs working in concert in a tightly integrated way where each one of them is actually solving problems in its sweet spot together for an overall application.
So you foresee in all this massive data center build-up we have with AI that more and more quantum computing are going in this data center?
Absolutely.
Timing?
Soon.
Okay. 2 years, 5 years?
I think sooner than 2 years.
Oh,
so I mean, I think you are seeing a lot of, including D-Wave, really get market traction with HPCs. So we sold an Advantage system, one of our annealing systems, to Jülich Supercomputing Center, which is a big HPC in Germany, and they actually are the host of the first exascale system in Europe. And they are investing heavily in really understanding emerging quantum computing technologies because they're really interested in how do we integrate these with our classical compute clusters. So.
Thank you. Here you have a very prestigious audience of corporate leaders or people representing the innovation arm for their corporation. In your mind, what are the things they should do to understand quantum computing and be ready for quantum? How should an organization be prepared for that?
Yeah, so the first message I want to deliver is that quantum computing isn't a future technology, it's here today. We have customers that are actually getting ROI on using our technology to fundamentally run and help solve hard business operations problems. So that the first sort of call to action is this is not a technology that's in the future, it's developing very rapidly and is here and is commercial today. I think there are a lot of opportunities for learning about sort of the state of the industry. We offer a very in-depth training session or training courses where if you want to actually learn about the industry in general and our technology in particular, it's a very good way to actually really understand the technology. And the third thing I want to emphasize is that this technology has moved out of the R&D phase, and the tools that exist for doing this development make it very easy for people to get up and running quickly.
I'm going a bit off track now. Sorry to surprise you. We had a very nice keynote of one of our senators. What about quantum computing in defense? And what about China? Where is the quantum computing technology development in China? And how do you see quantum computing playing a role in all this defense build-up?
Yeah, that's a really great question. I mean, at a high level, there are a lot of logistics and hard operation problems that come out of the defense industry. And we talked at our user conference, D-Wave user conference back in January in Boca. We have partnered with Davidson Technologies, and there is an Advantage system installed at Davidson Technologies. They're a defense technology company in Huntsville, Alabama, and worked with Anduril on a proof of concept that is very exciting in the defense use case. Again, hard optimization problems that we're delivering value on for those customers. So I do think that there's a lot of opportunity, and I think we're seeing a growing interest from the U.S. government in these technologies. Your question about China, I mean, this technology is, there are several agencies within the U.S. government who have labeled quantum computing as a critical technology and a technology that has national security implications. And so I think, it's very important that the investment and the uptake of this technology is really, really emphasized as much as possible. So.
And all this team is investing, and if the audience have to invest in quantum, which are the few sectors you would recommend them to direct their investment?
Yeah, so the applications development, I think, is critical. So that's really where we're seeing value today, and looking at sort of applying innovation funds that directly then drive a line of business is critical. So I think these technologies are commercial, and they're commercializing. The use cases that they can actually deliver value for are broadening, and so the investments really should focus on how do we set up corporations, enterprises to adopt these technologies as quickly as possible to gain the full benefit.
Now, thank you very much for this update. I would like to open the floor to questions. Is there any question in the room for Trevor? Remember, you have one of the best experts in the industry on stage, so don't be shy. And he flew from Vancouver. Oh, there's a question there. Yeah? Two questions there.
Just wanted to get your thoughts on cybersecurity and how quantum computing will be in that space.
Yeah, that's a great question. I mean, we've actually done a few proof of concepts around using our systems to train classifiers in the cybersecurity space. So, and looking at ways to build like more performant and tighter classifiers, which take basically a diverse set of data and then identify, whether there is a threat, whether there's been an exfiltration of data, and that I feel like that is an area where there's a lot of overlap between quantum computing and our ability to potentially enhance AI models. I think a lot of the focus from the cybersecurity industry on quantum computing is just the ability, as these systems scale, to potentially factor numbers efficiently. So this is an algorithm called Shor's algorithm, which really launched a lot of interest in quantum computing technology. I think that the hardware for actually doing something like breaking RSA is many, many years into the future. And the focus really should be on how do you actually integrate the existing capabilities to enhance current cybersecurity initiatives and to enhance basically operational resilience.
Thank you. I think there was a second question.
Yeah, it's over here. Yeah, thanks, Trevor, for the very good kind of question answers, and then Eric for the questions. So I'm very curious about for the quantum computing, because it's very good in like a drug discovery and kind of identifying new territories. Do you think that, what's your view on the applications in the physical AI, where like the data is actually getting very hard to get, very expensive to get, but then you have a ton of capital coming in, right? $1 billion investment in Army Lab and Leafy Phase World AI. So where do you see kind of the quantum computing coming in and potentially lower the cost for the data that we need to acquire in the real world?
Yeah, that's a good question. We actually completed a project in partnership with a customer, the pharmaceutical division of Japan Tobacco, and they had a workflow for doing drug discovery where they wanted to more efficiently generate molecular candidates that would feed into the pipeline that had higher quality than their traditional approaches. So they worked with us, and we developed a quantum hybrid machine learning model that learned their molecular data set and then generated higher quality candidates at the start of their pipeline. And they benchmarked this against the traditional only approach and saw that the actual quality that was entering the drug pipeline went up. So that's one example of a quantum classical architecture that is delivering more value in an AI or generative modeling application. Specifically, we think that our annealing quantum computing systems we know that they're incredibly good at generating high quality samples from distributions that can be trained or shaped. And this efficiency is what we are investigating and harnessing for AI models. And the promise really is you can actually train models with far fewer parameters and get the same results. You can reduce the amount of the compute cost at the inference stage, and overall try to shrink the growth of this computing requirement for running these models, both on the training and the inference side. So I believe we're early days with AI applications of quantum computing technology, but I think there are a lot of really, really exciting projects that are underway right now.
Trevor, I think there is no more questions. So thank you very much, and I hope that, thank you so much to be generous, visiting us and sharing your experience with the group. Thank you.
Thank you for the time.